Okay, is it better? Sorry, I thought that there were a sound, but unfortunately there weren't. Okay, sorry, that's my mistake. That you didn't have sound. Yeah, this means that you didn't have sound for the whole time. Okay, so again, we are learning for the merge sort. How the merge sort works: we take an array, split it into two halves, then we sort each of these sub-array recursively, and then you merge these two sorted arrays together. So we are trying to understand how to merge these two arrays together. Then let's start from the beginning. So kind of we have one pointer and one pointer here. So which element will be the first in the target array?
The smallest of the 2 pointers?
The smallest of these two, right? Yeah. So we take the smallest of these two, and for example, it was in A, we write it into array C and move the pointer here. Again, now you know that C already has an element there. C already has an element. Then you take two pointers here, so like you know that this element already is in the place. So again, which of these elements should be the next?
But the same logic.
Yeah, the same logic. It should be the minimum of them. So we take one by one. When we take an element from B, we move an index in B. If we take an element from A, we move index at A. So there is nothing very hard about that. So we write while E less than A and J is less than B. We do the following: if AI less than BJ, then we say C of L equals A of I, and then you move the left pointer. Otherwise, sorry, this is B. Else, we take B and increase, oh, and you also should increase L, of course. And you increase J and L plus plus. We are almost done, but not necessarily. Can you tell me why this algorithm will not work?
Oh, well, if one of the pointers reaches the end and the other array is the pointer in the other array didn't reach, then the remainder of this array will not.
Yeah, exactly.
The L array.
Exactly. So if one array has finished already, we should take the other array and put everything that is left into array C. So there should be while E less than A, then C of L plus plus equals to A I plus plus, and while J less than B, C L plus plus equals to B I plus plus. So yeah, so this is the case where their indexes are still not at the end, so we move them to the end. And you know that one of the cycles will be finished at the beginning because one already at the end. So the only one loop will be satisfied. So this algorithm, this merge algorithm, at first, what is the asymptotic complexity of this algorithm?
The whole algorithm of this function?
Yeah, this function.
This function is linear.
Linear what?
Of the sum of the, like, I mean, it doesn't matter, but the size of the array in
the sum of two input arrays. So it is sum of A and B.
Well, yeah.
Okay.
But like the input arrays are approximately half of each other size, so it's like a constant.
Yeah, that's true. So let us write the merge algorithm itself. So merge sort is simple. Then merge sort array A. Then we have array left, which is A over 2, array R A over 2 to A plus 1. Then we say L equals merge sort L, R equals merge sort of R, and then we return merge L R. So that's exactly what we did. We take the left part, we take the right part, we recursively sort them, and then you return. Why this merge sort will not work? What I forget? Any ideas? What I forget? Like in the recursive function, we talked about that last time, I think. So in the recursive function, when you calculate something, you should have a base.
Yeah.
Okay? We should have a base where to stop the recursion, because like it can go infinitely there. So what is the base here?
Well, if like for example there's only one element in the array or two elements.
Okay. Then we simply return an array back.
Yeah.
Okay, yeah. So if the size of the array is 1, then we return it. Okay, good. Let me see. Okay. Okay, this algorithm, like this is merge sort. Okay, yeah. Let's calculate the complexity of it. So suppose that merge sort works in M of A. Then, what is going on here? We split into two parts and recursively call over the halves. So it is 2 M A over 2 plus how much we should add? We do not have n here, but like this is the size of A.
Yes.
Yeah. So if you rewrite this exactly as like already said by our students, so like this will be like that. And we have to remember the theorem from the last lecture. We had the master theorem, which is said, you have to compare n in the power log BA with the last element here, which is m. So what we have here, what is A and what is B here in this recursive function? You have remembered the master theorem?
Yeah, like I don't remember exactly. It's, I think, let's suppose like A is the term in the fraction, the denominator, or is it not? And B is the term in the...
Yeah, so what it is?
Well, both two.
Both two, yeah.
Like, I don't remember which two corresponds to which constant.
Yeah, so A is here, B is here,
yeah,
but in this case they're equal, so you don't have to think about it. So you set log 2 over 2, it is 1, so this will be equal n. and then we compare their asymptotics of these two functions. They are equal. Then what will be the complexity of the algorithm? This is the second case. So there were three cases. One case when this guy was bigger than this one. One case when this guy is less than this guy, and there is a case where this guy is equal to this guy. So we're in the case where this guy equal to this guy. Yeah, you can look in your writing from the last lecture if you have.
It should be logarithmic.
Yeah, it should be logarithmic. So like, you have to take this complexity, which is n, and multiply it by a logarithm.
And n should be like, yeah, n should be raised to the power of 1 in our case, yes? Yeah. So, yeah,
So it is n over c, which will be n in the power of 1. Yeah, so it is n over in the power of c logarithm n, which is indeed n times logarithm n. Okay, so this is the merge sort. So there, then we think that you can write an algorithm kind of with faster complexities than of n logarithm n. Why so? It is very tricky, but it can be proven that suppose we only can compare two elements. So we have an array, and the only thing that we can do is to compare two elements. So like we can compare ith element with jth element. When you compare them, you have two options there. Either ai is bigger than aj, then you have one way, and then aj is bigger than an I. Okay, let me write it like that. So what does it mean? Suppose we are given all possible permutations. So we want to sort an array, and we are like, in general, how many different arrays we have that differs by their comparison? There are n factorial of them. So these are all different permutations, and we want to kind of sort them. So what you are doing, you're asking one. So here in the top, you have all n factorial arrays. Then you ask for one pair. You ask one pair. You compare ai and aj, and then you split them into two halves, kind of the whole field of all the permutations. You split into half, and that's all. Like you split into the half, one where ai less than aj, and one where ai is bigger than aj. And then you kind of, like, one comparison will split your their set of permutations onto halves. We don't know like where they're split into equal halves or not. We don't care. We know that it is split like at some two sets. So like then you compare some other in this case, then you compare some other in this case, and etc. And you finish when you have only one permutation in the set. This means that your permutation is sorted. Okay. So how many comparisons you should do? You know that one comparison split into halves at worst. So one of the part is, for example, this one is bigger than or equal than n factorial over 2. Like then you split again into halves, like half of them are bigger than n factorial over 4, and etc. So what is the maximal number of steps there?
Logarithm of n factorial?
Yeah, logarithm of n factorial, yes, good. Logarithm of n factorial. Can you tell me what it is? Probably you know from the math somewhere.
find is, well, asymptotically it's equals to like n of log n. No?
Yeah. So n factorial is itself is approximately n divided by e in the power of n. Like this is n factorial, like with some constant and like additional things, which we don't care exactly about, but like to be more precise, it is n factorial is like square root is 2 pi times n. But we don't care, we take the logarithm, so if you take the logarithm out of that, you will get exactly n logarithm. So this means that given only comparisons, you cannot do an algorithm better than n logarithm n. So our merge sort is kind of the best in the terms of complexity. The algorithm that uses only comparisons. Because we never used anything else, we used like the comparison here, and that's all. Okay, let us think about the following problem for a little bit. You know what inversion is? Okay, you don't know what inversion is, that's fine. So, suppose we're given an array A. An inversion is like one pair such that at I is bigger than AJ. So this means this pair is in the wrong corner. Okay? So, and the question is how to calculate the number of inversions using this algorithm, using merge sort algorithm.
Down to the merge function.
Okay, yes, good. We could think about merge function. Okay, and what we're doing there. Yeah, so
well,
here is nothing to change, right? So like we should go to the merge.
Yeah.
So
if everything is fine, if there is no inversion, then
yes,
probably those two halves, like it will go through the one array. And then we'll take the remainder as the whole another array.
Yes,
so it kind of has to do something with the pointers.
Yes.
So I guess else plus, maybe each else plus means inversion.
Yeah. So anytime. So what is inversion is that the element on the right is less than the element on the left. Okay. So what does it mean? Is that we have two pointers. So suppose that we are okay and the first element is fine. Then we could simply move the pointer to the right. There are no inversions because this is the smallest element and it will be on the left of everything. But then suppose an element B is less than this element. Then how many elements it has an inversion with?
B is less than the second element.
Yeah, B1 is less than second element of it. So it has an inversion over all elements here, right?
Yeah.
So you simply, when you point here, you just add inversions plus equal to A minus I don't know. Yeah, A minus Y. I think it should be like that. So you simply just like each time you see that element B is less than element A, we know how many inversions to this element there will be. And this is only in this merge. As you understand, we will calculate like this calculation means that in this array there were so many inversions per this element. Then when you go out of the recursion, you will have this element somewhere here, but still the inversions are there, like which we didn't calculate yet. There will be with the left part if you go out of the recursion. Okay, that's how you calculate the number of inversions in n logarithm n time. This is pretty interesting, since like the total number of inversions is squared, because like the totally unsorted array, like sorted in different order, will have squared number of inversions. And we calculated the squared number of inversions with n logarithmic n algorithm. So this is pretty interesting thing here. Okay. Another question. So not a question exactly, but this method of these pointers is named their method of two pointers. It is a pretty interesting technique. So let's try to solve the problem using that technique. You are given two sorted arrays, and you have to find such a pair of two, like the number of pairs, such that at AI plus bj equals to s, where s is fixed. So you are given two sorted arrays, and you have to calculate the total number of pairs such that the first element plus the second element are equal to s. This is their algorithm for two pointers exactly. So any ideas, probably?
We're given sorted arrays.
Yeah, we're given two sorted arrays.
Maybe we could move from the first end from the first array and from the beginning of the first array and from the end of the second array.
Mm-hmm. Okay, and what we're doing?
Just see if it is greater or equals to s, and if
Okay,
it's
and
greater,
what we're doing? Suppose that a, like this is p1, p2. Suppose that a p1 plus a p2 is bigger than s. What are you doing?
then we
Or
shall
b.
move, then we shall move the second pointer to the left.
Okay, good. And otherwise?
Otherwise, we should move the left pointer to.
Okay, yeah. So otherwise we should. So that's the main idea. We have two pointers, one on the left and one on the right, and we kind of since they're sorted, for the first array we find the position where we kind of split it between s. So somewhere here. Then we move like the position p1 to the right. Since it is increasing array, the position for the second array which splits on s somewhere to the left. So we kind of move the pointer to the left and so on. We move here to 1 and then move here to the left. And that is how you find the total number of pairs such that their sum is s. Okay. Questions up to the point? Great. Now we will learn another sorting algorithm, which is named Quicksort. it works in a little bit different manner than merge sort, but it is still divide and conquer algorithm. So like this type of algorithm names divide and conquer. Let me see. Okay, everything is fine, everything is fine. Okay, so we are given an array. And what we're going to do, we take the random element there, which is x, and we split an array into two parts. One each, to be more precise, in 3, but we consider that all the elements different, so like we don't have this issue anymore. So we split into less than x, equal to x, and bigger than x. And we know that when we do this, we have only recursively sort their elements only in these parts. And that's it. So you think, what differs the quicksort from merge sort? In merge sort, you kind of split, sort, and merge back. Here you just you split first into two parts, and then you sort them together. Like you already know that they're already in the sorted. These elements are already in the sorted order in their own part. So you already know that. So how to write this splitting algorithm? The idea is pretty simple. So we will add, so this is our array A, and we will go from left to the right by maintaining that, suppose we already process I elements, sorry. We already process these elements, and we maintain their split point. What the split point means, that this is less than x, and this one is bigger or equal than x. So here it comes the new element. Suppose it is bigger than x, bigger than x, what we should do?
Move to the next element?
Yeah, we just move this to I plus 1. Okay, good. Suppose that, so we have this I, and suppose the new element is less than x. What we can do? So we move to their I plus 1, okay, but we need to maintain the split point such that everything on the left is less than x and everything on the right is bigger than equal than x.
Well, we can move it towards that split point on the left side. We want the split point by one position.
And what we also do? Like here is the element, like the next element is bigger than x. We should do an additional operation there. So the answer is simple, right? We just
like we have to move everything.
We can just swap these two elements. We just can swap these two elements, and this element becomes less than x, and this element becomes bigger than equal than x, and we just simply can move this split point to the right. So that is how you split your array into three parts by that. And what is the positive thing about Quicksort is that you can do this in place. That you don't have to create, like previously for the merge, we created a new array where we copied the result. But here we don't have to do that. We calculate this inside one array. But there is a little difference. Also, there is another difference named stability. So, which we named, like, the sorting algorithms can be of two types: stable or not stable. What does it mean? Suppose that we have an array of elements one, A, N. And we know that there is somewhere lying the same elements. So X here, and X here. We know that these elements are kind of enumerated. So this is the first X, this is the second X, this is the third X. So their sort is stable if after the sorting, this axis will be in the same order. Why it is necessary, you could ask? This is necessary if you have, for example, objects or pairs where you have the key and the value, and then you sort them. You want the same pairs, like the pairs with the same key, will be in the same order as with the same values as they were previously in the array. So, for example, merge sort is stable algorithm. We can prove it because each time when we have merge, probably it wasn't stable, like exactly as it was there. But if, like here, ij, and if ai less than equal to bj, then we put ai in front. So kind of, if there are two equal elements, the first one will be the one on the left. However, the same is not possible here. Quicksort is non-stable algorithm, unfortunately. Okay. Oh yeah. Is it clear that, like, let's calculate the complexity of the quicksort. The complexity of quicksort, like calculating the complexity of the quicksort is much harder than calculating the complexity of the merge sort, since it is randomized. However, we will do right now a wavy explanation why it works in logarithm and logarithm and time. Suppose, like, if you will say that, like, it is Tn equals to, like, of n plus 2 times Tn over 2, you will be doomed. Why so? What is the probability of splitting an array into two halves of equal size?
It's like 1 over n, I guess.
Yeah, it is exactly. The middle element is 1 over n. Which is too low. We cannot argue that to split it into half. But can you tell me, suppose, like, what is the probability that the elements split into the following? So each part is bigger than equal than n over 3. So we kind of relax our proof a little bit, So instead of n over 2, we try to split it into n over 3 and the rest. So what is the probability that we split in such a manner that on the left there are at least n over 3 and on the right at least n over 3 also?
We need probability of either case, so the sum of all the cases. Maybe it would be 1/3.
Yeah, it is exactly 1/3 because like consider the sorted array, right? So which elements are fine to split into at least n over 3? So this element n over 3 plus 1, like this is sorted array. Blah 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 to n over 3. How many elements here? There are n over 3 elements. Thus the probability is 1 over 3. Because with probability 1 over 3, randomly choosing their position, we just get into that. So the probability right now is 1 over 3. Okay, good. Okay, good. Okay, and how many steps we should make to be sure, like in expectation, to be sure that we split into 3 times in at least these sizes? Like if the probability is 1 over 3, how many steps we should do in expectation to get their good split? Like it's easy. Yeah, it's 3. It's just like the probability of each one is like if you calculate the expectation, like the first success 1 plus success 2 plus success 3, their expectation of the sum is the sum of the expectations. So we can E S1 plus E S2 plus E S3, and each one is 1 over 3. So it is 1. So if you do 3 steps, the expectation number of our good split is at least 1. So this is exactly what we need. So that's why kind of the quicksort works in n logarithmic n time. So it is not exactly the good split. It is not exactly good split on 2 halves of the same size, but this is the split of at least worse, but still the complexity will be fine. That's the main idea. So like your kind of complexity will be here a little bit different. It will be n over 3 plus t to n over 3. Okay, so we already know 2 algorithms, 2 sorting algorithms, where one is stable with n logarithmic running time, and the other one is in place with n logarithmic n time, but randomized. Luckily, there is a way on how to do quicksort non-randomized, but this is a little bit more complicated algorithm, and I think it works worse than the randomized one. So like we will not care about it. The next problem that we will talk about is find a kith element. So we want without sorting the whole array, we want to find the element which will be kth in the sorted order. Luckily, Quicksort will help us in this. So suppose we want to find the kth element. We split an array in these three halves. So could you say where the kth element belongs to?
Well, when we select the pivot element, we could get lucky and it can be like our selected.
Yes, we
element.
can, but if we are not lucky?
Well, if it's smaller, then it's in the left part. If k is bigger than if k is smaller than our pivot element, then it's on the left side, and if it's bigger than the pivot element, then on the right side.
Not exactly as what you said, because we need to find kth element. We don't have to find the element k. We have to find kth element.
Well, kth element. Yeah.
So you just compare k with the size of the left of the left part, and if it is bigger than k, then this element somewhere here, because you know that they're smaller than everything on the right. So you should go there. Otherwise, if k is larger than that, you just subtract the length of this array and go into the right recursively. We know that with good complexity, so what is the complexity of this algorithm? It will be T of n equal, so some constant times n plus T of 2n over 3. Okay, because like this is exactly what we talked previously about. So kind of during 3 steps, we will get one of the parts is no more than 2n over 3. So can you tell me what this complexity is with this like recursive function? Let's think a little bit, and if it's not clear, we should make it clear. Okay, so let us, if it's not, let us do a quick math. So T of n equals to C times n plus T to n over 3. Okay. So let us open their second term again. So what it will be? It will be C times n plus C times 2 over 3n plus T to 3 squared times n. So if we open this again, we'll have Cn plus C to 3n plus C to 3 squared n plus T to third in the power of 3n. So if we will unfold this further, it will be equal to C times n plus C to 3n plus C to 3 squared n plus etc. So what is it equal to? What? Yeah, this is their the geometric sum. So it is 1 plus 2 over 3 plus 2 over 3 in the power of 2 and etc. It is constant because it is less than 1. So you will get some constant, I don't know, k times n. So the total complexity of the algorithm of finding kth element is often. So you did it like kind of we found the kth element faster than sorting the whole array. That's pretty interesting. Okay. Then a little remark. As we can see that both these algorithms, merge sort and quicksort, are working in n logarithm time, and we cannot achieve better by our theorem that if you are doing only comparisons, you cannot get faster complexity. But we can use not only comparisons. Suppose we have an array of elements, and we know that each element is less than m big. And m is, I don't know, approximately 100. And the length of A is approximately 10 to the power of 8. Like the first thing that you should understand by this values is that if A is very large, you cannot sort arrays very fast. Like it will take like a minute approximately. If you take the array of this length and you sort it using our algorithms with n logarithm. But we know that each element is less than 100. So what we can do?
Are those integers? Or
Yes, they are all integers. Yeah.
So we can make 100 buckets and place them there.
Yeah, exactly. You could have a bucket of 1 m, and when we see an element, we just zoom a. Sorry, this is bucket b ai plus plus. Then how to get the sorted array out of that? We just go from left to the right and output each element how many times it was there. So the total complexity of their algorithm will be of n plus m. Because like at first you go over each element and increment the corresponding position, and then you should traverse whole array of these buckets, which are m, and output each element once. So in total you will have n plus m. Okay, that's good. But suppose that now m is not 100 but 100 in the power of 3, for example. It is 10 to the power of 6. So you still can create m like 10 to the power of 6 and do fine. But suppose that we're not allowed to do so such a big array. For that, we will do the following. So like let's our array A. Let us split each element into digit parts. So kind of each element, like for example, in this case, will be on the two parts where each part is 100. So we kind of split each element into 3 integers. Each of them are less than 100. Like, is it clear how to do that? No questions. Okay, good. I don't know if it's good or not. But this is kind of like when you do this in binary expression, it will be 0 and 1s, and here it is not binary representation, it is 100 representation. So this one is modulo 100, this one divide by 100, take modulo 100, and this one divide by 100 2 times. Okay. What we will do, we will sort all their elements using our bucket sort. We first sort by their lowest bits. We first sort by the lowest bits. Then we sort by the second bit. And then we sort by the third bit. This is exactly where this table sort comes in play. Stable sort maintains the order of the pair of elements, of their equal ones. So here is, for example, I don't know, somewhere we're here 99, and somewhere we're here 99. And then after the first step, it will put 99 somewhere here together. 99, 99. Then we sort by the second order. So you will have suppose here is 3, and here 95, 90, or 90, 96, 95. This is 3, and this is 5. So after the second step, you will have somewhere, you will have like 99, 95 will be before 96, 95, 99, 99, 96. Here it will be 5, here will be 3. And then we sort by the topmost digit, and then your 3 will be before 5 afterwards. Why it is important to be stable? Because suppose it was 3 in both here. We sorted here, so there were 3. And we sorted here by 95 and 96. You see that this guy is on the left and this guy on the right. When you sort, like when you do a stable sort, you sort by the first element, and this guy will be earlier than this guy because it was to the left. And that is why you will get, like, if you have the stable sort, you will have this guy earlier than this guy in there after the third stage, after the third step. So this is named as digit sort. Because this is kind of by digits, right? So like we kind of get into the special representation of 100 here, for example, and we get stable sort, and consequently For example, here their complexity will be of n plus m, still m, like mr. If all the elements are m in the power of r, then the complexity will be like that. Like if all the elements are less than m in the power of r, then we sort them r times, because it has r digits in their m representation by the base m. So you sort r times, and each time you spend n plus m, so the total complexity will be n plus m times r. Okay. Questions? There we go to the one of the most important parts of algorithmics. So like sorting, to do sort you could ask, I don't know, arrays.sort or std colon sort or anything else. But you cannot do, you can of course, but like that will be a little complicated. Binary search. So suppose we are given a sorted array. And we want to find where here lies element x. Is there x in the array? For that, we start by the left point and the right point, which are out of the bounds. This is very important right now. So this is exactly out of bounds. Why we do that? This means that everything that is on the right are kind of for the infinity is bigger than x. Everything on the left is smaller than x. And we will maintain a specific invariant that left position always L corresponds to less than equal to x. And everything like to what R is pointing to is bigger than x. Like this is invariance. Okay, so L equals to -1, R equals to n, and we do binary search. What's happening here? Like how binary search works? We just have these pointers and we take their middle point. So we have these pointers and we stack in the middle. And we ask if this element is bigger than x. If it is bigger than x, then you should go to the left to search this element. If it is less than x, then x should be on the right. So kind of you split your array into two halves of equal size. So it was n, and then it becomes n over 2. And at some point you will have like L here, R here. Still you like have, so by the invariance, this one is always less than x, this one is also bigger than x. and we take the middle element and we compare it with x, and then you go to the left or to the right. So what's happening here? So L is on the left, so like our elements it's from 0 to n minus 1. So our left part will be out of bounds, and R will be out of bounds. This is not the problem of the algorithm because L plus R over 2 always will be inside the array. So we do while L and R are not near together. Like we will finish when then there will be such situation. So like left will be pointing to the next to the R, where this guy will be less than x, less than or equal than x, and this guy will be bigger than x. So we take the middle, so middle is L plus R over 2, and we compare. If A of m less than x, then we can move the left pointer to m, because we have an invariant that A of L, so again, remember, A of L is always less than x, and A of R is always bigger than x. So if A of m less than equal to x, then we can set L to m. Because if you set here, you will A of L less than x. Else, you will go to R equals m, so you move another pointer at the place. So you should remember how to write this binary search. It is very important to start out of bounds and then eventually get to the point. Okay. So suppose for a moment that there were several. Oh, I'm sorry. What is the complexity of this algorithm?
Logarithm.
Yeah, logarithm, since each time we split array in half. So this is logarithm. Okay, good. Now, suppose that we have an array sorted, and it will have x, 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 x. And we run this binary search algorithm. Can you tell me where will be L and R by the end of the algorithm? So we run algorithm on this array, we're trying to find x, and the question is where L and R at the end of the algorithm.
I think the L will be the rightmost element.
Yeah, exactly. Remember their conditions. L, elements of L, where L is almost less than equal to x. And R is bigger than x. So the first position which satisfies that, it is this one. So this is left, this is right. This will be at the end of the algorithm. There will be there. Okay, so this thing helped us to get the right, like the rightmost position of x. Okay, so, but for example, right now I want to calculate how many x's are in an array. So I ran the first binary search algorithm and it gave me the rightmost element. Can you tell me how to change this algorithm to get leftmost element?
We're going to change the condition.
How to change the...
So it would be a strict comparison in theoretically and non-strict in where it's strict now.
Okay, what should I change in the algorithm?
If A of m is less than x.
Yes.
If f of m is less than x, okay. And where will lie the leftmost x at the end?
In the R.
In the R, yeah, exactly. So at the end, if you do this, you will maintain the invariant that you change the invariant, so this is less than x and this is bigger than x. And that is why you get L here, which is less than x, and R here, which is bigger than x. So that is how you can get the leftmost and the rightmost elements, which are equal to x. Okay, good. Consider a little bit more complicated problem. So right now, like this is the kind of simple problem where you had to find an element in the array. Consider the following problem. You are having a street and you have a lights. You know that each, like, if we put a power x to the whole system, each light will, like, the radius of its light will be AIX plus BI. And the question is, what is the smallest x such that the whole street will be enlightened? So the first question, when you're stuck with finding something small or something smallest, you could think about binary search. What is the idea behind binary search? You have their continuous function in some sense. So it is like that. So it is false at the beginning, and then at some position it becomes true. For example, here, right? If we take x very large, larger than like this curvature point, then you will always lighten up the street. But if you are less than this point, the street will be not enlightened fully. So what are you doing? You start with x, like outer bounds, which is 0, and some infinity, for example, the length of the string, which is L. Then you do while L minus R less than R minus 1, and you maintain the following invariant. This is never enlightenment. And this one always enlightened. And again, we are doing the same. We take the middle value and check if satisfying, if M satisfies, if M satisfies, then what should I do if M satisfies? Kind of if for M we could walk over whole.
We should set the R to?
Yeah, we should set R to M because R is always enlightenment. So we set R here and we set left here. So, and at the end, you will get two consecutive positions, L and R, where L is not enlightened and R is enlightened. So the R will be the smallest. Okay. An interesting question, which is kind of orthogonal to this, is how to check, like given X, how to check that the street is fully enlightened.
exactly are we given here? Are we given an x? And
We're given x, and we know that the street light, the street lamp, enlightens with the radius ai x plus bi, where x is the thing that we ask it, we put into the function. We want to check whether all the street lights cover the whole length of the street.
and we're given like a single x. So
What?
Can't we just like calculate the sum in itself? That's it.
Unfortunately, sum is not good since they can cover like this, right? They can intercept. Okay, that's another technique, to be honest. Let's, for each light, we'll have two events. We'll have event, there is a light in, so like +1, and there is light out, -1. Let's take these positions and sort them. So we will have some array where is this xi plus -1. So we have like this. We have an event at position x. We either create a new line, kind of we have a light, or at position xi we stop having a light. Then we just go from the left to right using pointer technique. So we take one by one. And we consider, is there, like here, in between, is there a light there? If there is, we are fine. If there are not, then we lose. And that's it. Yeah, of course we have here 0, 0. Nothing happens. So we start from 0, 0, and like we are going from the left to the right. Just maintaining this environment that at each point in time there should be at least one light, and we calculate how many lights are covering this segment. Okay, good. This is binary search, but we consider it right now the binary search for the integers when we were like where our answer is integer. However, the answer is not necessarily integer. For example, in this problem, we could ask x to be some rational or some irrational number. I don't know. How to do that? Like, one could think that we can do like that while r while r minus l bigger than epsilon, then do this. While the difference is small, and you want to find the precise answer, so you kind of do a binary search of their until this becomes epsilon. But there is a problem, a little bit of problem. Suppose that R and L are very large. And your precision is, I don't know, 10 to the power -3, or 10 to the power -5. if R and L are very large, then their difference is not necessarily large, unfortunately, because there is no enough precision for the double there. Because if L and R itself like 10 to the power of 380, something like that, there will be like the double numbers are maintained like especially in the word. So like it is I don't know how it's in English. So like there is the main part and kind of 10 in the power of 42. I don't know. Like it is maintained as the small value times 10 in a large in the power, and you store this thing and the power. The problem is that if you take like R and L, which are very large, the difference between R and L will be not less than some small number. It will be pretty large. That's the main issue. So this is how you should never write where you want to get a precision, where you want to get a precise answer. So one way is to do that. It is while true, we take m equals L plus R over 2, and if m equals to L or m equals to R, then break. What does it mean? It means that L and R are consecutive double numbers. This means that like the middle between them, it is either L or R. Because there is no double in between. This is one step, and this is one way, and which I really prefer mostly. It is where you just say for iterations from 0 to 100. You just do this hundreds of times. And you don't care exactly of their precision. But after 100, you will approximately get what you need, because like 100 is 2 in the power 100. So it is good enough precision. Good enough precision for us to get left to right. So the same could happen if, for example, you have a problem that you have an increasing function and you want to find the zero position. You can see that this is exactly the problem for binary search, because it was less than 0 up to some point, and then it becomes bigger than 0. So it's kind of the true-false function. On the left it is false, and on the right it is true. Then you can run binary search on that in order to find. You just kind of have left here and right here. And you just maintain the invariant that left is always less than 0, f of L is less than 0, and f of R is always bigger than 0. And you just jumping by that, you will be getting to the proper position. Okay, we have a small amount of time. So are any questions about binary search? You will have some problems in the homework, which are on binary search. Okay, so an additional thing that I should to tell you, there is in the Google Doc where you have, which I've sent you, there will be like there are number of tasks which are obligatory. So you have to solve these tasks to pass the course. If you haven't solved this task, then unfortunately you are kind of doomed. So you don't have to solve all their homework, but you have to solve at least the problems that are written there. So please, like the last time, it was quite hard for the students because they were put in this, like, because the deadline are by the day of the exam, and everybody just think, okay, we will do this before the exam, like nobody cares. And then before the exam, like they spent like by 2 weeks by solving these problems, or less than 2 weeks, I guess, but still it took them time to solve the problems somewhere in January, which I do not think is right, while you have other exams. So the last thing that I want to talk with you today is ternary search. This is an interesting problem. It is similar to binary search, but it is a little bit different. So it helps us to solve the convex problem. What does it mean? So you have a function that decreases to some point and increases afterwards. But you don't know. So in binary search, if you know this function, you can do the binary search there. For example, if it is convex function, you just can take the second derivative, which will be less here, and the second derivative which will be higher. No, not the second, the first derivative. The first derivative will be less than 0 here and larger than 0 here. But if the function is not necessarily continuous, then it helps to find, like the ternary search helps to find the lowest point of this. For that, we will have like 3 pointers, again, left and right, 2 pointers. And instead of 2 points, we will ask for 3 points. We will have the point to L plus R over 3 and L plus 2R over 3. And we compare. So this is M1, this is M2. If f of M1 is larger than f of M2, then we could say that left is M1 and R is M2. Otherwise, R. L equals to L and R equals to M2. Why so? So consider that M1 is here and M2 is here. So we know that M1, like function of M1 is bigger than f of M2. Then your smallest point lies somewhere here. Why do I understand that? Because suppose that, so if M1 is kind of before this curvature, then M2, it is less, it is somewhere here. Here, or here, or here. But if M1 is on the right, here is M1, it can never be greater than the function of M2.
Sorry for that, we have lesson here right now.
Already right now? Where is your teacher?
Nikolai.
Where he is? Okay, so, sorry, wait. So we have M1 here. and M2 will be higher. And that is why you have the second case, kind of you take M2 here and L here. Okay, does it make sense? So you kind of, you always, by choosing this condition, you always have that your lowest point is always somewhere between L and O. And that's all, and that's it. And after like 100 of iterations or something, you will have that L and R will be somewhere inside there. Okay, questions? Okay, no questions? Then we are done for today. Thank you very much for coming.
Thank you.